In this video, we're going to learn how to derive the Duhem-Margules equation. Now, the Duhem-Margules equation is actually an equation that relates the vapor pressure of components of ideal solutions with the mole fractions of the constituents that there are within that solution. Now, we need to use the Gibbs-Duhem equation in order to find out the Duhem-Margules equation. So this is the Gibbs-Duhem equation. You have NA d mu A plus NB d mu B, and that is equal to 0. So this is the Gibbs-Duhem equation. Now we need to use it to find out what the Duhem-Margules equation will look like. Now the first thing I need to do, I need to take this component and take it to the other side of the equation. So that is going to look like this. We have NA d mu A, and on this other side we're going to have negative NB d mu B. Now the question is, what is N sub A? What is N sub B also? And d mu A and d mu B, what are they? So this is actually the number of moles of the constituent which exists within that particular ideal solution. So let us say you have an ideal solution within this container and it's made up of basically two components. That is A and B. Now obviously you are going to have the amount of the first component as well as the second. So N sub A actually stands for the amount of the first component, and N sub B, that stands for the amount of the second component. Now this stands for the derivative of the chemical potential of the first component, and this stands for the derivative of the chemical potential of the second component. What is the formula for chemical potential? Now the chemical potential of any entity is actually equal to the standard chemical potential. So that will be mu naught plus R, that is the universal gas constant, multiplied by the absolute temperature, multiplied by the natural logarithm of the vapor pressure. Now this is actually going to be the partial pressure that we will use as an equivalent as we try to solve for each component. Now before we go there, let us continue with the derivation. So the next thing I need to do on this equation, I need to take the total form of the number of moles, which obviously will be, that will be N sub T, and that should be equal to N sub A plus N sub B. So if I took this and divided through this whole equation, this is what we're going to have. N sub A divided by N sub A plus N sub B d mu A. And on this other side, we're going to have N sub B divided by N sub A plus N sub B d mu B. Now this is what you need to know. If we are talking about the mole fraction of components within any entity or mixture of gases, that is actually represented with an X, with the subscript representing the component or the constituent of that gas. Now this would stand for N sub A divided by N sub A plus N sub B. This is the mole fraction of the first component within that container. So we can also have another. This will be N sub B, N sub A plus N sub B. So this will be the mole fraction of the second. Now what I'm going to do, instead of using N sub A divided by what you have below there, I'm actually going to use X sub A. So this will give me something like this. On this other side, we're going to have a negative X sub B d mu B. So that is what you have over there. So let us call this equation, equation 1. Now next up, we need to work some things. We know that the mole fraction of the first component is A. And the mole fraction of the second component, that is X sub B. Since we know that the mole fraction of the first component is written as N sub A divided by N sub A plus N sub B, that is obviously going to give us a fraction in it, because we actually have a lower number on top as compared to what we have below the fraction or the numerator. Let us say the number of moles of the first component was something like 1. This is a 1 plus, let's say this is actually a 2. You're actually going to find 1 divided by 3, which is obviously something that is less than 1, right? Now we know that the number of moles of the second component, which is actually B, is 2. So here we're going to have N sub B divided by N sub A plus N sub B. This is going to give us something like this. This will be 2 divided by 1 plus 2, which is actually going to give us a 2/3. So you know that if we add this with this is going to give us a 1. So that says the whole story we're trying to put out here. If you took the first mole fraction and added it with the second, that should give you 1. So that is basically the idea I'm trying to relate in this step. So if we have this, we could say also that X sub B is the same thing as 1 minus X sub B, right? Now this particular form, we're actually going to use it to solve some things. If you wanted to differentiate each component or each term within this equation, you actually need to use the polynomial rule of derivatives. So if I wanted to differentiate this part by partial derivatives, that is going to give me something like this. So that will be partial X sub A. And this is a 1. And that is a constant. If you actually wanted to differentiate a constant, that will give you 0. So on this part, we should have a 0. Now how about this one? You have a negative X sub B, which in this case is actually going to be taken as a variable. So if you wanted to differentiate that, that should give you a negative partial X sub B. So differentiating this form gives you a negative D X sub B. So you need to hold these also at the back, very important. Now the next thing I'm going to do, I would actually take up this first equation and divide it by the derivative of X sub A. So that will be X sub A d mu sub A. This is equal to X sub B d mu sub B. So this will be divided by d X sub A, and on this side we're actually going to do the same thing. Now there is actually something I want to do. We know that dx sub A, that is the same thing as negative dx sub B. So in this case, I'm actually going to take the other side and replace it with a negative dx sub B. Now why I'm going to do that is because I really want to have a kind of homogeneous form of the expressions on both sides. On this side, we actually have all values being in the variables of A. And so on this other side, we're also going to try to have that. So that should be a negative dx sub B. So that is going to be x d mu sub A divided by dx sub A. And on this side, we're going to have a negative x sub b d mu sub b, and here this would actually be divided by negative d sub b. Well, negative dx sub b. Now in this case, we can find that there is a negative on top as well as 1 below there. So that pretty much is going to change to a positive. Now I can wipe this out. So this should be x sub a d mu sub a, and this will be divided by dx sub a. And here now we're going to have a positive. So this should be x sub b d mu b divided by x sub b. I need to wipe this out also. Now, what is the next thing that we need to do over here? So for this part, I'm just going to call this the second equation. Bear in mind, we actually had a first equation. Now this is the second. Feel free to rewind the video and find out what is the first equation. Now from here, we need to move to the chemical potential of a component within an ideal solution. Now this is the formula for a chemical potential. You have it as mu, and that is equal to mu naught plus RT ln P. Now this P, this actually stands for the vapor pressure. But you could also have it as the vapor pressure for one part of a solution or a mixture of gases, as well as in total form. So in this case, we're actually going to split it and have it in terms of the first constituent as well as the second. So we have A and B being the components of the gases which are present within the ideal solution that we're actually looking at. So in terms of A, we should have something like this. This will be mu sub A, and this is going to be mu naught. Now notice this is not actually going to have a subscript, because this is actually the standard of chemical potential. And so that is always the same value regardless of whichever component you are actually dealing with. So this remains the same way. And this is going to give us ln P sub A. So in this case, we're actually talking about the partial vapor pressure of the first constituent. How about the second? What is it going to be? So that is going to be mu sub B, and this is mu naught plus RT ln P sub B. Now, these are the two forms of the chemical potentials of the two constituents within these ideal solution. Now what I'm going to do next is I will take each of these equations and differentiate them as much as possible. Now on this other side, we actually have a linear form or a polynomial form of the subject. Here we have a mu A, and that is equal to mu naught plus RT ln PA. And here we have a mu B, that is equal to mu naught plus RT ln PB. So what I'm going to do, I will take the first one. Let's say this is equation star. Let this be equation star star. So equation star, let me use that to differentiate it. So I think I'm going to wipe this part out. Yeah. So if I wanted to differentiate this form, what is that going to give? So this should give us mu sub A, and on this side I'm going to have the derivative of this form. Now we already said that this form is actually a constant, so if you were to differentiate a constant, that should have given you a 0, right? So that becomes a 0 and reduces to none. So here now we're going to have the derivative of RT ln PA. So this will be d RT ln P sub A. Now we know also that R and T, they are actually constants, but in this case they are multiplied with the variable. So we might not well want to call them as constant ordinarily. They will be called coefficients. So in that case, we're going to bring them out and have d mu A being in this form. This is RT d ln P sub A. So this is the form that we need to keep. Now let us try it for the other one. If we tried it for the second component, that should give us something like this. This will be dRT ln PB, right? And so d mu b is equal to RT d ln PB, right? So this will be the second. This is the second equation. And the next thing I need to do, I need to take all these equations and plug them back into equation 2. And that is actually reasonable, because in this place you actually find that there is a d mu a as well as a d mu b, right? And from these forms we have a d mu b as well as a d mu a. So I'm just going to change the d mu a as well as a d mu b, which we have in equation 2, and replace them with these other forms. So substituting this and this into equation 2, this is what we're going to have. We would have x a, and d mu a in this case will be replaced as RT d ln PA. And this is divided by dx sub a. And on this other side, we have a d mu b, which is actually RT d ln P sub b. Okay, and this is divided by dx sub b. Now you can actually find something which is common on both sides of this equation. We have RT being common on this side and also on the other side. So what is that going to give? That will cause this to cancel out and cause the equation to reduce to this. So we have x a multiplied by d ln P sub a, and this divided by dx sub a. On this other side, we're going to have x sub b multiplied by d ln P sub b divided by dx sub b. Now we're actually going to use this later on, but I need to create out some precedents right now, which we'll actually use to substitute back into this highlighted equation. Now, if I had d ln xa, or let me take it back. Let's say you had a y, and y is equal to ln x sub a. If you have this function and you are required to find the derivative of it, what is going to give? What is that going to give? So you are actually going to have dy of dx sub a, right? Because in this case, I'm actually differentiating this partially, and that is the reason why you see the partial derivative form. So that shouldn't actually take your attention. What we are interested in is the formula for solving the natural logarithm of this variable. Now, if you wanted to solve this, this is going to give you 1 divided by x sub a. Now, we know that y is the same thing as ln x sub a. So instead of writing this, I'm actually going to replace this with this form. So that will be d ln x sub a divided by d of xa. This is going to be 1 divided by xa. Next up, I will cross multiply using each form of each side of the equation. So this goes to multiply with this part, and this will multiply with 1. So this is going to give us x sub a and multiplied by d ln, this should be an x sub a And on these other side, we're going to have a 1 multiplied by a dxa, which should actually give us a dxa basically. Now, you know that we actually have an x sub a as well as a dxa within the highlighted equation. So what I want to do, I want to make this stuff to look like this. I want to change this and create a form that looks like this on this other side. So how can we do that? What is the step that we need to take to bring that to be? So I need to take this part and divide through the whole equation by it. So this is going to be x sub a d ln x sub a, and here we're going to have a dx sub a divided by a dx sub a. On this side also, I'm going to have a dx sub a. Now obviously this cancels out. This is going to cancel out, and we're going to have this stuff. Now next up, I also need to change this part. I need to change the position of d ln x a. I want it to be on this other side. I want it to be on the other side. Because what I want to have, I just want to have an x sub a divided by a dx sub a. So you're actually going to have something like this. And this will be multiplied by d ln x sub a, and this will be obviously equal to 1. So I need to take this part to the other side. That is to isolate the xa dxa, which I have. So that is going to give us an x multiplied by 1 dxa, and on this other side we're going to have a 1 divided by d ln x a. Right? So we already have that form from the highlighted equation. So we can actually take this part and, we should take this part rather and replace it into this form. Now this same thing which you have done for the first part of the ideal solution, which is actually for the first component, that is for the A constituent, you can also do that for the second one. So if I wanted to do that for the second one, basically the answer should be this way. I should have an x sub b multiplied by 1 divided by dx sub b, and this will be equal to 1 divided by d ln x sub b. That is what I'm going to have. So we already have those forms here. We already have them. This is for the first component, and this is for the second. So what I will do now is to change the positions, or replace these forms rather, with what they are on the other side of the equation. So this is what we're going to have. I'm going to have 1 divided by d ln xb multiplied by d ln pa. And this will be equal to 1 divided, I made a mistake there. This is actually supposed to be an a. Okay, so this will be d ln xb multiplied by d ln pb. Yeah. So bringing back together, this should give us d ln p sub a divided by d ln xa. And this will be equal to d ln p sub b divided by d ln x sub b. This form is actually the equation of the Duhem-Margules equation. This is what we were looking for. Now, what if you were asked to integrate this form? If you integrated this equation, this is what you're going to have. For the first component, which is the partial pressure for the first one, you're going to have a P naught that is a P naught of A, which is actually partial pressure for the first component in a pure state. That is multiplied by the mole fraction of the first component, and multiplied by e raised to the power of alpha multiplied by x squared of the first. Rather, this should give the second component. Now, if you wanted to find it for B, that is the second component, then you would actually have something like this. This would be the partial pressure for the pure component in the second case. So we should have a B here. And this will be multiplied by exponential alpha x raised to the power of 2 sub A. So notice there is a B here whilst there is an A here. And on this other side there is an A whilst there are B's on this side. So that is actually what you're going to have if you were asked to integrate the Duhem-Margules equation. So this is the integrated form. And this is the Duhem-Margules equation. And so with that, we have come to the end of this video.